Take a glass of water, just an ordinary glass, the kind you drink from every morning without a second thought. Now look at it. Not at it, I mean really into it. Because I want to tell you something that nobody told me in school, something that took me years of thinking to really sit down with properly. And it is this: inside that glass right now, there are processes happening that produce temperatures hotter than the surface of the sun, not in some laboratory with superconducting magnets and billions of dollars of equipment, right there in your kitchen. In the glass of water, you're not finishing because you got bored halfway through breakfast. I can see it on your faces. You think I'm exaggerating. You think this is one of those scientist tricks where we say something dramatic and then immediately walk it back with, well, technically speaking, on a microscopic scale. No, I'm not walking anything back. I'm going to tell you the absolute unvarnished truth. A collapsing bubble of water under the right conditions, which are quite ordinary conditions, by the way, can briefly generate temperatures that rival the surface of a star. And if you'll stay with me for the next hour or so, I think you're going to find that the explanation for why that is the case will take us on the most extraordinary journey through the nature of matter, the nature of energy, the nature of time itself at the smallest scales. And we are going to start, as all great detective stories must start, with a crime scene. The crime scene in this case is a ship's propeller. It is the year 1894. The British Royal Navy has just commissioned a new torpedo boat destroyer called HMS Daring. Wonderful name for a ship, by the way. And they're taking her out for sea trials. She's supposed to hit 30 knots. She doesn't. She barely hits 22. The engineers are baffled. They pull the propeller out of the water and they find it covered, absolutely covered in pits and craters, like someone took a ball-peen hammer to it. The propeller is being eaten alive, and nobody knows why. The propeller was being destroyed by something invisible, something nobody had a name for yet, a violence born from silence, from the simple act of water trying to fill an empty space. They bring in Osborne Reynolds, a brilliant engineer and physicist, a man whose name you probably know if you've ever taken a fluid mechanics course, because the Reynolds number is named after him. Reynolds looks at the propeller, does his calculations, and says, the propeller is spinning so fast that the pressure on the backside of the blade drops below the vapor pressure of water. Now, what does that mean? It means the water locally, right behind the blade, effectively boils. Not because it's hot, because the pressure is so low. You see, water doesn't boil only when you heat it. Water boils when the pressure around it drops enough that it can no longer stay liquid. Lower the pressure enough and water will boil at room temperature. Lower it enough further and it will boil at 5 degrees Celsius. The propeller was creating little patches of vacuum as it spun, and into those patches water was flashing into vapor and forming bubbles. Thousands of bubbles, millions of bubbles. And then, and here's where things get interesting, as the propeller blade moved on and the local pressure returned to normal, those bubbles collapsed violently, catastrophically. The shock of their collapse was pitting the steel of the propeller like it was made of soft cheese. Reynolds named this process cavitation, from the Latin cavitas, meaning cavity or hollow space. And the Navy said, right, thank you very much. That's a terrible inconvenience for our propellers. Fix it, please. And for the next 50 years, that's essentially how the world thought about cavitation. It was a nuisance, an engineering problem to be solved. Nobody was thinking about what was actually happening inside those collapsing bubbles. Nobody was asking, what is the temperature inside a bubble at the moment it collapses? What is the pressure? What is the physics of that tiny, violent, microsecond event at the scale of a fraction of a millimeter? I want you to think about why that question wasn't being asked, because it tells you something important about how science works. When something is a nuisance, we try to eliminate it. We focus on the outcome, damaged propellers, and we try to engineer around the cause. We don't always stop and say, wait, there is something extraordinary happening here that I don't understand, and I should understand it, not because it will help my propellers, but because it is one of the most violent and bizarre events in all of classical fluid dynamics, and it happens inside a glass of water. Science goes wrong, I think, when it becomes only a servant of immediate utility. The most beautiful discoveries, the ones that change them. Everything they almost always start with somebody asking a question that has no obvious practical application, asking it purely because something strange is happening and strange things deserve explanation. So let's ask it. Let's actually ask what happens inside a collapsing bubble. And to do that, I want you to picture something for me. Imagine you have a tiny sphere of vapor. Let's say it's about 1 millimeter across, which is actually quite large for a cavitation bubble. But let's start there. The vapor inside is at low pressure. The water surrounding it is at higher pressure. The bubble is being squeezed from all sides simultaneously by the weight of the water around it. Now, and pay attention here, because this is where the magic lives, the bubble begins to collapse inward. The walls are converging toward the center, and they are converging from all directions at once. This is a spherically symmetric implosion. Now, I want you to think about what happens to the energy in that system. The water surrounding the bubble has pressure. Pressure times volume gives you energy. As the bubble collapses, the volume decreases. That energy has to go somewhere. Where does it go? It concentrates. It focuses. The collapsing sphere is essentially a lens for energy. And just as an optical lens takes parallel rays of light spread over a large area and focuses them to a tiny brilliant point, the collapsing bubble takes energy spread over its entire spherical surface and focuses it to the center, to a single point, or rather to an incredibly tiny volume at the center. Now, here's the thing about focusing energy. When you concentrate energy into a smaller and smaller volume, you get higher and higher energy density. And high energy density means high temperature. This is not magic. This is just thermodynamics. The gas in the bubble is being compressed at extraordinary speed. And when you compress a gas fast enough that it doesn't have time to exchange heat with its surroundings, what physicists call an adiabatic compression, then all that mechanical energy goes directly into raising the temperature of the gas. You've seen this yourself, actually, if you've ever used a bicycle pump. The pump gets hot as you compress the air inside it. Same physics. But a bicycle pump is gentle. A collapsing cavitation bubble is doing the same thing, but it's doing it thousands of times faster, and it's doing it from all directions at once. And the geometry of spherical convergence means the energy concentration at the center is almost beyond imagining. When the bubble's wall reaches the speed of sound in water, about 1,500 meters per second, it's moving so fast that the gas at the center has no time to respond. The compression happens in a blink that is itself inside a blink, with Salfadit in Dick and Zion de Zior. Let me give you some numbers, because numbers are important. They're how we separate genuine understanding from poetic hand-waving. The initial temperature of the vapor inside the bubble, around room temperature, let's say 25 degrees Celsius or 298 Kelvin. The initial radius of the bubble, perhaps 0.5 millimeter. The final radius at collapse, a few nanometers, maybe less. We're talking about a radius ratio of roughly 100,000 to 1. And when you do the calculation, and I'm going to spare you the differential equations right now, though they are beautiful equations and you should learn them someday, you find that the temperature at the center of a collapsing bubble can reach anywhere from 10,000 to over 1,000,000 Kelvin. 10,000 Kelvin is roughly twice the temperature of the surface of the sun. 1,000,000 Kelvin is in the range of the sun's corona. We are talking about stellar temperatures. Inside a bubble of water. In your kitchen. Now you're shaking your heads, I can see it. Some of you are doing the calculation in your heads and you're thinking, wait, how can a bubble of water contain something hotter than the sun, even briefly, without, vaporizing the entire ocean? And this is a beautiful question, and it has a beautiful answer. The answer is the energy is there, but it is confined to an unimaginably small volume for an unimaginably short time. We are talking about a temperature spike that lasts somewhere on the order of nanoseconds, billionths of a second, and that occupies a volume perhaps a few nanometers across. A nanometer is a billionth of a meter, so the total thermal energy is extraordinarily concentrated. But the total amount is actually very small. It's like having a firecracker versus a bonfire. The firecracker, in the instant of its explosion, releases energy at a rate, a power density, that rivals a nuclear explosion. But there's so little of it that it doesn't burn the house down. It's the briefness and the smallness that save you. The intensity is real. The scale is tiny. But here's where the story gets really strange, because in 1934, a physicist named H. Frenzel and his graduate student H. Schultes at the University of Cologne were doing an experiment with ultrasonic waves in water, high-frequency sound waves, the kind we now use in medical imaging. They were driving these waves through water, and they noticed completely accidentally that the water was emitting flashes of light, tiny, tiny flashes, barely visible in a darkened room. They called the phenomenon sonoluminescence, from the Latin sonus, meaning sound, and luminescence, meaning light, sound into light. They published their findings, there was some mild interest, and then the scientific community essentially did what the scientific community sometimes does with observations it can't explain. It set the problem on a shelf and walked away. The shelf sat there for decades, and then in 1989, a physicist named D. Felipe Gaitan, working with Lawrence Crum at the University of Mississippi, did something that seems in retrospect almost absurdly simple. He took a single bubble of air and trapped it in a flask of water using ultrasound. He made the sound waves drive the bubble through rhythmic cycles of expansion and collapse at the same frequency as the sound, and this single lonely tiny bubble began to flash. Not occasionally, continuously. Every single cycle, every expansion and collapse, it emitted a flash of light, a repeating, pulsing, single bubble light source driven by sound. They called it single bubble sonoluminescence. And it completely reignited interest in the whole phenomenon because now you could study it in a controlled, reproducible, measurable way. And what they measured was astonishing. The light flashes had a duration shorter than 50 picoseconds. That's 50 trillionths of a second. To give you a sense of scale, 50 picoseconds is to 1 second as 1 second is to 630 years. In 50 picoseconds, light travels about 1.5 centimeters. These flashes were almost impossibly brief, and when they analyzed the spectrum of the light, the distribution of colors and wavelengths, they found it was consistent with blackbody radiation at temperatures of between 10,000 and 100,000 Kelvin. This was not estimation. This was measurement. A bubble in a flask of water, driven by sound, was producing temperatures at its center comparable to the surface of a star and briefly emitting light accordingly. 50 picoseconds. This is how long the light lasts. In that time, a beam of light travels less than 2 centimeters. The universe barely has time to notice it happened. Now I want to pause here because we have arrived at something genuinely mysterious, and I don't want to rush past the mystery in my eagerness to explain. I want you to feel the mystery first, because the mystery is the best part. When you understand why something happens, the thing itself becomes a little smaller in your mind, a little more domestic, a little more tamed. But right before understanding, when you're standing at the edge of the explanation with the full strangeness of the phenomenon still in front of you, that's when science feels like art. So stay with me for a moment in this not knowing. A glass of water, ordinary water, you drive sound waves through it. Bubbles form and collapse. Those bubbles briefly, and for 50 trillionths of a second, contain something hotter than a star's surface. Why? Not in a how does this happen technical sense, but in a deep physical sense. Why does the universe permit this? Why does the mathematics of fluid dynamics and thermodynamics conspire to create this extraordinary concentration of energy in such an ordinary setting? It seems, how do I put this? It seems almost excessive. Like the universe is showing off. Like nature built into the architecture of matter and energy this extraordinary capability, and it sits there quietly in every glass of water, every swimming pool, every drop of rain, waiting for the right set of pressures to briefly demonstrate that the cosmos operates at a scale of drama that we, walking around in our macroscopic comfort, have no everyday access to. All right, now let's get into the actual physics more carefully, because I've been talking in pictures and I want to now talk in principles. The first principle I need to give you is the Rayleigh-Plesset equation. Don't be scared by the name. Lord Rayleigh, the same Rayleigh who explained why the sky is blue, the man had a knack for being involved in every beautiful problem in physics. Lord Rayleigh first worked out the mathematics of a collapsing spherical bubble in 1917. He was thinking about, of all things, propeller damage. The Navy again. He wanted to understand the pressures generated when a bubble collapsed and impacted a solid surface. He derived an equation, a beautiful nonlinear ordinary differential equation that is satakam yukwamai sakai to dizizumam ypreismajmajnin that describes how the radius of a bubble changes over time as a function of the pressure inside and outside the bubble. What Rayleigh found, and what is still remarkable today, is that the velocity of the bubble wall increases without bound as the radius approaches zero. If you solve his equation for a perfectly spherical bubble collapsing in an incompressible fluid with nothing inside, true vacuum bubble, wall velocity goes to infinity. This is obviously unphysical. Real bubbles don't collapse to a true mathematical singularity. The gas inside the bubble can't be compressed to zero volume. Quantum mechanics and intermolecular forces eventually push back. But what this tells you is that the mathematics of spherical bubble collapse is inherently singular, inherently extreme, in a way that is built into the geometry. The convergent sphere is a compression machine of almost unlimited violence, restrained only by the physical properties of real matter. The key insight, and I want you to really hold on to this, is that the violence of the collapse comes from the geometry, not just the energy. Let me make this very concrete with an analogy. You are sitting in a stadium. There are 50,000 people in the stadium. They all make noise. A huge, diffuse noise that reaches you as a general roar. Now imagine all 50,000 people simultaneously focusing their voices at a single point, whispering in perfect unison, like a laser of sound, aimed at a single location. What was noise becomes unbearable intensity at that point, not because there is more total energy, but because it is focused. The geometry of focusing is what creates the intensity. The collapsing bubble is the same. The energy comes from the surrounding water pressure, which is nothing extraordinary. It's just the ambient pressure plus whatever ultrasonic driving you've applied. But the spherical geometry focuses that energy to the center, and the convergence is so extreme that ordinary energy becomes extraordinary energy density. Now, there's another element to this story that I find just as fascinating as the temperatures, and that is the timescales, because the physics happening inside a collapsing bubble is not just extreme in space, it's extreme in time. The collapse from full size to minimum radius takes somewhere between 10 and 100 microseconds, millionths of a second. But the final phase of collapse, the last few percent of the radius reduction, happens in picoseconds. This is faster than the speed of sound in water. I want you to really understand what I just said. The bubble wall in the final moments of collapse is moving faster than sound can travel through the surrounding water. This means the water around the bubble cannot communicate with itself quickly enough to respond to what's happening. You get shock waves. The bubble doesn't just quietly collapse, it implodes with a supersonic shock that propagates outward through the water. That's part of why cavitation damages propellers. It's not just the heat, it's the shock wave, a tiny explosion repeated millions of times per second. I told you there would be a historical story in here, and I want to give you a good one, because history of science is not just interesting gossip. It's actually a window into how ideas grow and how errors get made and corrected. The physicist I want to talk about is a man named Seth Puterman, a professor at UCLA, who in the 1990s became, not exaggerating, obsessed with single bubble sonoluminescence. Obsessed in the best possible scientific way, the kind of obsession that means you come to the lab at midnight and leave at 3 in the morning. Not because someone is making you, but because the phenomenon won't let go of you. Puterman and his group were measuring the spectra of sonoluminescence, the distribution of light frequencies, and they were finding results that were genuinely strange. The spectrum was continuous, like a hot body glowing, which implied very high temperatures. But there were also some hints of spectral lines, specific frequencies of light that would be produced by specific atoms or molecules, and some of those lines were unusual. There was a paper published in the late 1990s, not by Puterman's group, that claimed to detect spectral signatures that were inconsistent with any known chemical process at temperatures below hundreds of millions of Kelvin. Hundreds of millions. That's not just stellar. That's approaching nuclear fusion temperatures. The claim was that perhaps inside a collapsing bubble, nuclear fusion, the same process that powers the sun, was occurring briefly. They called it bubble fusion, or more provocatively, tabletop fusion. The scientific community went a little crazy. If you could get nuclear fusion inside a collapsing bubble in a flask of water, the implications for energy, clean, limitless, fusion energy, were staggering. Papers were written, press conferences were held. And then, in the careful, grinding way that science actually works, not the dramatic TV version where one genius reveals the truth, but the slow institutional version where dozens of labs try to reproduce results and mostly can't, the claim fell apart. The spectral lines in question turned out to be experimental artifacts. The temperatures were certainly extraordinary, but they were in the range of tens of thousands to maybe a few 100,000 Kelvin, not hundreds of millions. No fusion. But here's what I find beautiful about this episode. The scientists who made the incorrect claim were not frauds. They were following a genuine strangeness in the data, a real puzzle with real excitement. They got the scale wrong. The temperatures they found were extraordinary enough to mistake for something even more extraordinary. That is a measure of how strange the phenomenon genuinely is. It was strange enough to be mistaken for nuclear physics when it was only stellar physics happening inside a bubble. The temperatures were so extraordinary that scientists mistook them for something even more extraordinary. This is not a failure of science. It is the highest compliment nature can pay to those who look carefully. There is, I should say, one serious scientific claim in this territory that has not been fully resolved, and I want to be honest with you about it because I think it's important to distinguish what we know from what we don't know. A researcher named Rusi Taliakan at Purdue University published papers in 2002 and subsequently claiming that in a particular experimental setup with special deuterated acetone, not water but a different fluid, he was seeing evidence of nuclear fusion from bubble collapse. The claim was disputed, investigated, reinvestigated. There were allegations of data irregularities. The scientific community's verdict was largely skeptical. I'm not here to adjudicate the specifics of that controversy. What I will say is this: I don't think it's crazy to wonder whether, under the right conditions, the violence of bubble collapse could approach nuclear fusion scales. The physics doesn't absolutely forbid it. But the evidence for it happening in any experiment performed so far is not solid, and in science we believe the evidence, not the idea, no matter how beautiful the idea. Now I want to pull back even further and talk about what sonoluminescence tells us about something more fundamental. The relationship between the microscopic and the macroscopic, the quantum world and the classical world in situations of extreme energy density. This is the deep water, philosophically speaking, and I want to swim in it with you for a few minutes. We live in the macroscopic world. We deal with objects we can see, touch, push, pour. In that world, water is just water. It flows, it splashes, it supports boats, it conducts heat. It behaves according to the equations of fluid dynamics, which are perfectly classical, perfectly Newtonian, perfectly deterministic, in the sense that if you know the initial conditions, you can calculate the future. But inside the collapsing bubble, in the last few picoseconds of collapse, when the temperature is tens of thousands of Kelvin and the pressure is millions of atmospheres, the water is not just water anymore. The molecules have been dissociated, torn apart into their constituent atoms. The atoms themselves have been ionized, their electrons stripped away by the violence of the thermal collisions. You no longer have water, you have a plasma, a soup of bare atomic nuclei and free electrons smashing into each other at speeds proportional to the square root of the temperature. A miniature, incredibly short-lived stellar interior. And in a plasma at those temperatures, quantum mechanics starts to matter in ways it doesn't for ordinary room temperature water. The radiation, the light that is emitted, is not just the simple result of hot things glowing. It involves the quantum states of electrons, the transition probabilities between energy levels, the way electromagnetic radiation is emitted and reabsorbed in an optically thick plasma. This is atomic physics and plasma physics operating at the boundary between classical and quantum regimes. And honestly, we do not have a completely satisfying theoretical model that accounts for every feature of the sonoluminescence spectrum. There are still open questions. The field is not closed. If you are a young physicist in this audience, or even a not young one, this is a problem that could still use a really good mind applied to it. I want to say something about open questions in physics because I think we scientists sometimes do the public a disservice by presenting the world as more understood than it is. You read the textbooks and everything seems so settled, so organized, so complete. Chapter 1, Mechanics, Chapter 2, Thermodynamics, Chapter 3, Electromagnetism, everything fits, everything has an answer, and then you actually get to the frontier of knowledge and you find that it's not like a completed jigsaw puzzle at all. It's more like a jigsaw puzzle where you've done a lot of the middle, but you can't even see the edges and you're not sure how big the board is, and half the pieces you think are in the right place might need to be moved later. Sonoluminescence is a great example of this. We understand a lot. We can explain the basic mechanism. We can calculate rough temperature estimates. But the precise spectral features, the detailed dynamics of the plasma state, the question of whether quantum vacuum effects, the Casimir effect, zero-point energy fluctuations play any role in sonoluminescence, these are genuinely unsettled. Smart people disagree. The experiment is hard to do precisely. The theory is hard to calculate precisely. This is science in the real, as opposed to science in the textbook, and it's beautiful precisely because it's unsettled. The unsettled parts are the growing edge, the living tissue. The settled parts are the skeleton, important, structural, but not where life is happening. I want to do one more thought experiment with you because I think it really captures the strangeness of what we've been discussing. I want you to think about the concept of a focusing structure in physics. The universe is full of focusing structures, arrangements of matter or geometry that concentrate energy from a diffuse state into an intense local state. A magnifying glass is a focusing structure for light, takes the dilute energy of sunlight and concentrates it enough to ignite paper. A parabolic radio telescope dish is a focusing structure for radio waves, takes faint signals from billions of light years away and concentrates them at the focus point. A gravitational lens, a massive galaxy acting as a natural telescope. Focuses light from even more distant objects by bending it through curved space-time. These are all focusing structures operating at wildly different scales, from centimeters to billions of light years. A collapsing bubble is also a focusing structure, a four-dimensional one actually, spherical in three spatial dimensions and with a specific temporal dynamics driven by the differential equations of fluid collapse. The bubble wall is the lens surface, the center is the focal point, the energy of the surrounding pressurized water is the diffuse input, the stellar temperature plasma is the focused output. And this focusing structure is not exotic, not engineered, not rare. It forms spontaneously, automatically, inevitably, anywhere you have a liquid with supersaturated dissolved gas, or a rapidly moving surface that drops the local pressure, or ultrasonic waves propagating through a fluid. It forms in every glass of water that has ever been rapidly stirred. It forms in the oceans, in rivers, in your blood vessels, in very mild forms that don't produce starlight, obviously, but the same physics, the same equations, the same geometry. The focusing is universal. The scale varies. Only in extreme cases does the focus reach stellar temperatures. But the principle, the basic mechanism of spherical convergent focusing of fluid energy, that's everywhere. It's woven into the fabric of how fluids behave. And this brings me to something I find genuinely moving about physics. And I don't use that word lightly because physicists are supposed to be hard-headed calculators who don't get moved by things. But I am moved by this. The fact that the same mathematics and the same equations, the same geometric principles, the same thermodynamic logic describes a bubble in a flask of water in a laboratory in California and the interior of a star burning in the Milky Way. That is not a coincidence. That is a discovery. It is the discovery that nature does not invent new rules for different scales. It uses the same rules everywhere, and the richness of reality comes from applying those same rules in different conditions, different initial configurations, different boundary constraints. The star is big, the bubble is small. Both are governed by gas dynamics, by the adiabatic equations of state, by the compressive heating of confined gases, by the radiation physics of hot plasmas. Same equations, same physics, different scales. This is what physicists mean when we talk about the unity of nature. Not that everything is the same, but that everything is variations on the same deep theme. The equations that describe a star burning in the galaxy are the same equations that describe a bubble collapsing in your kitchen. The universe does not change the rules depending on how closely you're watching. Now, let me bring you back down to earth, or rather, let me bring you back to practical things, because I know some of you are sitting there thinking, this is all very beautiful, Feynman, but what is sonoluminescence actually good for? Is it useful? Can it do anything? And the honest answer is, we don't fully know yet. We're still in the phase of understanding it. But let me tell you what the promising applications look like, because they're interesting. The most obvious is cleaning. Ultrasonic cleaners, the little baths you use to clean jewelry or surgical instruments, work by cavitation. You drive ultrasound through a liquid, generate billions of microscopic cavitation bubbles, and when those bubbles collapse near a surface, the shock wave and the microjet that forms at the moment of asymmetric collapse, because real bubbles near surfaces don't collapse symmetrically, they collapse asymmetrically, sending a high-speed jet of liquid into the surface. The jet scours the surface at speeds of hundreds of meters per second. This is a remarkably effective cleaning mechanism. It reaches into crevices that no brush can reach. It operates at room temperature, and it's purely no chemicals required. This is mature technology. You can buy an ultrasonic cleaner for $30. It works via the same physics that pits battleship propellers. The same violence, domesticated, miniaturized, made useful. There's also pharmaceutical and medical applications. The microjets produced by asymmetric bubble collapse near cell membranes can temporarily permeabilize the membrane, poke tiny holes in it, allowing drug molecules to enter cells that would normally resist them. This is called sonoperation, and it's being studied as a way to deliver chemotherapy directly into cancer cells. You attach drug molecules to microbubbles, inject them into the bloodstream, aim ultrasound at the tumor, and the bubbles collapse at the tumor site, depositing the drug directly. Targeted drug delivery via controlled cavitation. Beautiful. Brutal and beautiful at the same time. And then there is the long-shot dream, which I mentioned earlier, sonnefusion, the idea that perhaps bubble collapse could reach nuclear fusion temperatures and be used as an energy source. Most physicists are quite skeptical of this for practical reasons. Even if occasional fusion events occur, the energy balance seems very unfavorable. You put in far more acoustic energy than you'd ever get back as fusion energy. But I wouldn't want to completely close the door on it either, because the history of physics is full of things that seemed practically impossible until someone found a clever way to make them work. I hold the question open, not with great optimism, but with appropriate humility in the face of a phenomenon that has already surprised us many times. I want to say something near the end here about what I think we actually learn from phenomena like sonoluminescence beyond the specific physics. I think we learn, or should learn, something profound about our intuitions and where they fail us. Human beings are adapted to understand the world at human scales. We understand objects we can hold, processes that last seconds or minutes, temperatures between the freezing point of water and the hottest summer day. Our intuitions are calibrated for this range, and they serve us fine for most of everyday life. But the universe operates at all scales simultaneously, at the scale of quarks and at the scale of galaxy clusters, at timescales of Planck time, and at timescales of the age of the universe, and at every scale that is not the human scale. Our intuitions are essentially useless guides. They don't just give the wrong answer. They don't even give us the right questions. 50 picoseconds, a temperature of 100,000 Kelvin, a radius of a few nanometers. These numbers don't mean anything to your gut. Your gut doesn't have a feel for them. The only tool we have for navigating these scales is mathematics. And this is why I've always felt that the most important education a scientist can have, and maybe the most important education anyone interested in understanding reality can have, is mathematics. Not because mathematics is abstract and cold and separate from the warmth of human experience, but precisely because it is the only language that doesn't lie about scales. The equations don't become confused when you ask about very small numbers. They don't panic when the answer has many zeros in it. They follow the rules wherever the rules lead, even when they lead somewhere that sounds utterly impossible, like stellar temperatures inside a millimeter-sized bubble. I sometimes think the universe must find it very funny, if the universe could find things funny, that we evolved on a small rocky planet under a medium-sized star and calibrated our entire perceptual apparatus to deal with the narrow range of scales between things I can see without squinting and things I can see without a telescope. And then we invented science, and science kept pushing the boundaries of what we could observe and measure and calculate, and every time we pushed past the comfortable human scale, the universe turned out to be stranger and richer and more surprising than we could have guessed every time without exception. That track record should, I think, fill us with something, not anxiety, not humility exactly, but a kind of electric anticipation. If everything we've looked at closely enough has turned out to be stranger than we expected, what do you think is sitting quietly in the things we haven't looked at closely enough yet? In the phenomena that are right now labeled as nuisances or side effects or engineering problems and haven't yet been asked about deeply, what strange physics is waiting in those unsolved corners? I started with a glass of water. I want to end there too, because I think there is something deeply important about the fact that we are talking about water, not a particle accelerator, not a supernova, not a neutron star where we'd expect extreme physics. Water, H2O, the most ordinary, most essential, most democratically available substance on Earth, the stuff that covers 2/3 of the planet's surface, the stuff your body is mostly made of, the stuff you drink without thinking, pour without ceremony, step over puddles of without wonder. Inside this ordinary substance, given the right pressure, the right frequency of sound, the right configuration of a tiny bubble, is the capacity for temperatures that would vaporize any material you've ever encountered, for pressures that would crush any submarine ever built, for the brief, violent, magnificent reconstitution of plasma physics in a space so small that you could fit 10,000 of them across the width of a human hair. All of this is there in the water, always. The physics doesn't go away when you're not looking. The mathematics doesn't take a day off. The same equations that describe the sun's corona are always, at every moment, potentially being enacted in the fluid dynamics of the liquid in front of you. And so, I want to leave you with this thought. The next time you look at a glass of water, try, just for a moment, to see it not as a transparent, refreshing, ordinary thing, but as a medium that contains multitudes, a medium in which violence and beauty coexist at scales you cannot perceive, a medium that under pressure, under stress, under the right kind of agitation, will briefly recreate the interior of a star in a space smaller than a speck of dust. The ordinary is not ordinary. The mundane contains the extreme. The everyday cup is full, not just of water, but of physics that most of the universe doesn't even witness. You witness it. It's sitting right there. And the universe, if it could wonder about such things, might find it rather remarkable that there's a species of upright primates on a small rocky planet who have, after a few thousand years of science, figured this out. That's worth something. That's worth a lot, I think.